Welcome back to my channel. I am Jumana Khanfar from Taqarrub International Schools. In this lesson we will study energy. Energy is either mechanical or non-mechanical. Non-mechanical energy is like the thermal energy or heat when it is transferred between objects, nuclear energy or chemical energy, the energy stored in the chemical bonds, or the mechanical energy. The mechanical energy is either potential or kinetic. Potential energy is the energy stored in an object because of its position or its shape. We're going to study two types of potential energy: gravitational potential energy and elastic potential energy. Gravitational potential energy is the energy stored in an object because of the force of gravity. This object here is placed at a height h from the ground. Then the potential energy stored in this object is proportional to the height. The higher the object, the more the potential energy stored in it. That's why when you release this ball, it goes down to reach what we call the equilibrium. It goes down because there is potential energy stored in it, and this potential energy is converted to kinetic energy as you release it. We will discuss that later. The other type of potential energy is the elastic potential energy. Elastic potential energy is the potential energy for springs, for example, or rubber bands or bungee cords, for those elastic things. As you stretch the spring to the right, potential energy will be stored in that spring. That's why when you release it, it goes back in the opposite direction. Now, the other type of mechanical energy is the kinetic energy. Kinetic energy is the energy of moving objects. Whenever the object is moving, it has kinetic energy. This is the formula we use to calculate the kinetic energy. Kinetic energy is equal to half times mass times v squared. So the kinetic energy of an object depends on the mass and on the speed squared. Energy is a scalar quantity. Scalar quantities don't have direction, they just have magnitude, like distance or time or mass, while vector quantities have direction, like force, like the weight, the displacement, the acceleration, and these things. So energy is either mechanical or non-mechanical. Non-mechanical is like thermal, nuclear, chemical, and other types. Mechanical energy is classified to two main categories: potential or kinetic. Potential energy is the energy stored in an object because of its position or its shape. An example of the potential energy is the gravitational potential energy, the energy stored in an object because of gravity. It depends on the mass of the object, the acceleration of gravity, which is constant as you are on the surface of Earth, and the height h from the equilibrium point. The other type of potential energy we're going to study in this lesson is the elastic potential energy. It's associated with elastic materials like the springs, the rubber bands, bungee cords, any elastic material. As you stretch or compress that elastic material, potential energy will be stored in it, and it causes the restoring force. It's calculated by this formula, half kx squared. K is the spring constant, or we call it the force constant for elastic materials. Each elastic material has a specific constant. X is the displacement of the object. It's the difference in length. For example, if the length of the spring is 10 centimeters, if I stretch it to 12 centimeters, X will be 2, the difference in length. So it's half kx squared. In order to understand the different types of energy and how they are related to each other, we need to solve the following examples. The first example is about a pendulum bob. A pendulum initially at rest, so Vi is 0, the initial velocity is 0. Or let's call it Va because it's at point A. The object starts here at point A. is released and swings through points B and C. It's moving in this direction. What types of mechanical energy are present at points A, B, and C? Now let's remember the different types of mechanical energy. We have the kinetic energy, Ke, or just simply K. This is equal to half mv squared. The potential energy is either gravitational or elastic. But here we don't have an elastic material, so it's all gravitational. So this is Ug. Ug is equal to mgh. At point A, if we assume that point C is the point of equilibrium, the lowest point in the system, so this is 0, the height at this point is 0, then A is at a height h from point C. Then there will be gravitational potential energy at point A. So at point A, we have Ug, it's equal to mgh, and Ke at this point is 0, the kinetic energy, because the velocity at this point is 0, and according to the formula, if you multiply anything by 0, it's 0. So at point A, the kinetic energy is 0, and the potential energy is mgh. Could be calculated if we find, if we have the height and the mass of the object. At point B, Ug is equal to, again, mgh, because it's above the equilibrium point. So this is mgh again, but the height is less than the height at point A. So we have less potential energy at point B. And Ke is not 0 at point B because the ball is moving, so it has velocity. Therefore, it has kinetic energy. It's half mv squared, whatever the velocity at point B is. Now at point C, it's the lowest point. The height at this point is 0. So we can say that Ug at this point equals 0 because it's mgh and h is 0 here. Ke is equal to half mv squared because the object is moving at point C and it will continue its way up to the maximum height here. So there is velocity and it is the maximum. What formulas could be used to calculate the total mechanical energy at each point? The total mechanical energy, or sigma E, is the sum of Ug plus Us plus Ke. I mean, it's the sum of all types of mechanical energies. So at this point, sigma E is the sum of Ug plus 0, so it is Ug. Then sigma E at this point, or the total mechanical energy, is Ug or mgh. At point B, we have them both, so sigma E, or the sum of the total mechanical energy, is mgh plus half mv squared. At point C, Ug is 0, so sigma E is equal to half mv squared, just the kinetic energy at this point. A ball has mass and speed and therefore has kinetic energy. What is the effect on the kinetic energy of the ball when its speed is doubled? For such example, when we don't have numbers, it's all about symbols. You need to write all the symbols you have, then find the formula that relates them all to each other. Then you can change the value as mentioned in the question. A ball has mass m and speed v, and therefore has kinetic energy. We have Ke. What is the effect on kinetic energy? How will the kinetic energy change of the ball when its speed is doubled? When v is 2v. When a value is doubled, it means that this value is multiplied by 2. Like when v is 3, if you double it, it's 6, and so on. Now, firstly, before we change the value of v, we need to write a formula of Ke with m and v. We know that the kinetic energy is equal to half mv squared. Now, as I change the speed, the kinetic energy will change. If I multiply the speed by 2, 2v all squared, the kinetic energy will be multiplied by 4 because 2 squared is 4. Again, if I replace V by 2V, this is going to be a new kinetic energy. Now 2 squared is 4, so this is going to be 4V squared times M times half, and this is Ke star, the new kinetic energy. We need to compare between this formula and the previous one. The difference is that this formula is multiplied by 4. So Ke new is equal to 4 times Ke, the original one. Actually, this example is simple, but if you have any other examples with the same concept, you can firstly write the symbols down, then write the formula that relates them all to each other. Then you can change the variable that is mentioned in the question. Another important topic for the SAT test in physics is the conservation of energy. The conservation of energy principle states that energy can neither be created nor destroyed. So, energy is always conserved in an isolated system. If the system is open, then it's not conserved because it can go out and in of the system. But for isolated systems, energy is always conserved. So when you solve any problem, the amount of energy present at the start of a problem must remain constant throughout the entire problem. It means that the total mechanical energy, sigma E at the beginning, I, equals the total mechanical energy finally at the end. You must consider some important properties of energy to understand conservation of energy fully. Energy can transform from one type to another, like from potential energy to kinetic, as we will study later. Energy can transfer from one object to another. Energy can leave and enter a closed system as work. And in the next lesson, inshallah, we will study work and power. So you will understand the relationship between energy and work. So, to apply the conservation of energy principle, we apply this formula. Sigma E initial equals sigma E final. Sigma E means the total mechanical energy, or Ke plus Ug plus Us. This is equal to, again, Ke plus Ug plus Us final, and this is initial. It looks hard, but when we start solving the questions, you will see how easy it is. You just add all the energies at the beginning, and that's equal to all the energies at the end of the problem. If this ball is released from rest, it means that the kinetic energy at this point is 0, because if you remember, kinetic energy is equal to half mv squared, and Ug equals mgh. At this point, Ke is 0, but the potential energy Ug equals mgh. As the object goes down, the height decreases, so Ug decreases, and the speed of this object increases, so Ke increases. So that decrease in the potential energy is an increase in the kinetic energy. Let's assume that the kinetic energy here is 0 while the potential energy is 100, for example. At this point, if the potential energy is 40, the kinetic energy is 60, because the sum will stay 100 as at the beginning. As the ball reaches the ground, the height is 0, so Ug is 0. What will the value of Ke be? What do you expect? Of course it is 100 if we assume that no energy is lost in the way down, because the total energy stays the same at all the points according to the conservation of energy principle. So at this point the total energy is Ug. Here at this point the total energy is Ke plus Ug. At this point the total energy is Ke because the object has its maximum speed here at the time it touches the surface of ground. Same here. At this point when you hold the pendulum bob, the velocity is 0. So the kinetic energy is 0. As you release it, the velocity increases, while the potential energy decreases to reach 0 at this point because it's the lowest point. The potential energy at this point is converted into kinetic energy. That's why the object has higher speed here, so it can apply a force on the next bob to move it. Actually, I assume that you know the difference between speed and velocity. Velocity is speed with a given direction, while speed is a scalar quantity. It does not have direction. So when I say speed, it means the magnitude of the velocity in this case. This is an example of all the previous ideas. A boy standing on a ledge throws a ball with a mass of 0.5 kilograms. So the mass of the ball is 0.5 kilograms. Straight up into the air with an initial velocity of 20 meters per second. So the velocity at this point is 20 meters per second. The ball is initially 5 meters above the ground. The initial height of the ball is 5 meters. It rises to a maximum height. So this is the maximum height, and as we know, the speed at the maximum height is 0. And then falls, missing the ledge on the way down. The ball impacts the ground 5 meters below its initial starting point. So the ball starts here and it will impact the ground here, 5 meters below its starting position. What is the total mechanical energy of the ball as measured from the ground? The total mechanical energy, or sigma E, is equal to Ug, which is mgh, plus Ke, which is half mv squared, and there isn't elastic energy here, elastic potential energy. I can find the total mechanical energy at any point, and according to the conservation of energy principle, it is the same at all the points. But I choose a point where I know enough information to calculate the total mechanical energy. At point A, I know the height and the speed. The height is 5 meters and the speed is 20 meters. So I can calculate sigma E. Sigma E is the mass, which is half. G is 10. And the height is 5. Plus half. The mass is half again. You can write it as 1 over 2 or 0.5, it's okay. And the velocity at this point is 20 squared. Don't forget to square it here. Half of 10 is 5 times 5 is 25, plus 20 squared is 400. Half of 400 is 200. Again, half of 200 is 100. And this is 125. Now, what is the unit of energy? Energy is measured in joules. So this is 125 joules. Then the total mechanical energy is 125 joules. B. What is the total mechanical energy of the ball 2 meters above its release point? 2 meters from this point, what is the total mechanical energy? As we said, the total mechanical energy is the same at all the points. So again, it's 125. This is somehow tricky. Some students just start to calculate it and they don't have enough information. They need to calculate other things to be able to calculate it. You just need to know that it is the same because it is conserved. What is the maximum height reached by the ball as measured from the ground? Now we need the height at this point, where we know the velocity is 0. So to calculate the height at this point, let's apply the formula of sigma E again at this point, but here we know the value of sigma E. So we can find the other variables. Now at this point, sigma E is 125 again, because it's the same at all the points. The mass is 0.5, G is 10, the height is unknown, plus half times the mass 0.5 times the velocity at this point, which is 0. So all of this term is 0 because when you multiply 0 by any number, the result is 0. Now 125 is equal to half of 10 is 5, h. Divide by 5, so h is equal to 25 meters. So the height from the ground to this point is 25 meters. And notice that it's not the height from the starting point here, it's the height from the ground because we found the total mechanical energy from the ground. So this is 25 meters. D. What is the impact velocity when the ball reaches the ground? We need the velocity at this point. Let's call it V final. Now you can apply the kinematics equations to find it, because you have the acceleration, the initial velocity is given as well, and the height or the displacement. But here let's apply the conservation of energy formula. Sigma E equals mgh plus half mv squared. We already calculated sigma E at the starting point, so we can just substitute it here as 125. M is 0.5, G is 10, and the height is 0 at this point because it's the lowest point. Plus half times the mass, again half, times v squared, which is the unknown. Now this is all 0 because 0 times any number is 0. Then we have 125 equals half of half is 1/4. Let's write it as 1/4. It's easier to deal with fractions because on the SAT test you're not allowed to use the calculator. Now let's do the cross multiplication. 4 times 125 is 500. 500 is equal to v squared. Take the square root for both sides. Square root of 500 is square root of 5 times 100. This is v. 5 is not a perfect square, so just leave it as square root of 5. And square root of 100 is 10. This is equal to v. It's measured in meters per second. So the velocity at this point is 10 radical 5 meters per second. This was pretty hard, so let's go to other easier questions. A 0.02 kilogram pendulum bob is released from position A. As the pendulum passes position C, here, located 1.25 meters below position A, so the distance between A and C is 1.25 meters. What is its velocity? So we want the velocity at point C. B at point C is missing. And the height is given from point C, which is the lowest point, to point A. To be able to calculate the velocity, we need to find the total mechanical energy at point A and the total mechanical energy at point C and compare them. Sigma E at point A equals sigma E at point C. Energy is conserved. Sigma E at point A is mgh plus half mv squared. And this is equal to, again, mgh plus half mv squared at point C and at point A. For point A, because the object is released from rest, the velocity is 0. At point C, because it's the lowest point, the height is 0. So mgh is all 0. Always when you write the total mechanical energy for the maximum and the minimum points, one term will be cancelled for each. This makes the question easier actually. mgh is equal to half mv squared at point C. M and M could be cancelled out. G is 10, H is 1.25, and this is equal to half V squared. 10 times 1.25 is 12.5, and this is half V squared. Multiply both sides by 2 to cancel the half. This is 25 equals V squared. V is square root of 25, which is 5 meters per second. This is a new idea here because we have a spring. So we have US, the elastic potential energy. A 1 kilogram block, the mass of this block is 1 kilogram, moves with a speed of 10 meters per second. This is VI. So the mass is 1 kilogram. VI at the beginning is 10 meters per second. And strikes a spring that has a spring constant of 25 newtons per meter. This is K, the spring constant of the spring, newtons per meter. Determine the maximum compression of the spring. We need to determine the maximum compression of the spring, which is the displacement of the spring, and that's X. Now, to be able to calculate the maximum compression of the spring, we need to write the formulas for the total mechanical energy for points A and B, the initial mechanical energy and the final mechanical energy. Sigma E initial equals sigma E final. Sigma E initial is mgh plus half mv squared plus half kx squared. This is US, this is UG, and this is KE. And this is equal to half mv squared plus half kx squared plus mgh. There is no change in the height, so mgh is the same at both points. So we can cancel it out. At the beginning, at this point, the spring is not stretched and not compressed. So the displacement is 0. Then I can cancel out this. At the maximum compression, as the mass compresses the spring to its limit, the velocity is 0. So half mv squared at point A, or at the beginning of the motion, is equal to half kx squared when the spring is compressed. We can cancel the halves. M of the mass is 1. V squared is 10 squared, which is 100. And this is equal to K, 25x squared. Divide both sides by 25 by 25. X squared is equal to 4. Then x is equal to 2 meters. So the maximum compression of this spring in this problem is 2 meters. I know this lesson is somehow long, but be patient. This is the last problem. And we have a new idea here, so you need to focus. Energy lost by non-conservative forces. Sometimes as the object moves from one point to another, some energy will be lost. And this is what happens in real life, because you cannot move an object from one point to another without losing energy, because of friction, for example. A 50 kilogram sphere starts at rest. The velocity at this point is 0, then the kinetic energy is 0 as well. Skis down a 5 meter tall hill inclined at 30 degrees. The sphere arrives at the bottom with 2000 joules of kinetic energy. The kinetic energy at this point is given. It is 2000 joules. And we know that the potential energy at this point is 0 because it's the lowest point. The height is 0 at this point. How much energy was lost due to friction? We need to find the lost energy. Now let's apply the conservation of energy formula again. Sigma E initial equals sigma E final. Sigma E at this point is half mv squared again plus mgh minus E lost, because some energy will be lost from the total energy at the beginning. If it's not mentioned that there is friction or some energy is lost on the SAT test, don't use this. Apply it without subtracting the lost energy. Now this is equal to the total energy at this point, which is given 2000 without applying any formulas. We said that the kinetic energy at the beginning is 0 because the velocity is 0 as the object started at rest. mgh, the mass is 50 kilograms, g is 10, and the height is 5. Minus E lost equals 2,000. 50 times 10 is 500. 500 times 5 is 2,500. Minus E lost equals 2,000. So E lost is 500 joules. 1/5 of the energy was lost because of friction. That's all for today. I hope that you enjoyed this long lesson. There is a worksheet in the description box below. You can upload it and check if you understood the lesson well or not. In the next video, we will study work and power and study the relationship between work and energy. See you next time.